At this point, we've established that entropy equals the reversible heat at a given temperature, and that when we can treat the surroundings as a reservoir that can give or take heat without changing temperature, then the change in entropy is equal to the negative change in enthalpy at that temperature for the system, for a process at constant pressure. What if we have two objects in thermal contact at two different temperatures, but there's no other actions? If we can treat the process in isolation, then the heat transferred from one will equal the heat transferred into the other. We just don't know which one is which. To set up the situation, we say that the change in entropy of system 1 is the absolute value of the heat transferred into or out of system 1 at the temperature of system 1, and the same thing for system 2. Because the absolute values of the two heats are the same, we can say that the change of entropy of system 1 at temperature 1 is the same as the change of entropy in system 2 at temperature 2. And with a little arithmetic, we have an equation for the change in entropy of system 1. So let's say that we want the heat to flow from system 1 into system 2. Then the change in entropy of system 2 minus the change of entropy in system 1 has to be greater than 0 for this process to go from reactants to products, or from initial state to end state. We have to say it's the end state minus the initial state, and the change in entropy for the total process has to be greater than 0. Now we can sub in our equation for the change of entropy in system 1 into this equation, and again with a little bit more arithmetic, we can cancel out the change in entropy altogether and find that the temperature of system 1 has to be greater than the temperature of system 2 for heat to flow from system 1 into system 2. And this is why, all else being equal, heat will flow from a high temperature object into the low temperature object and never the other way around. But what happens at the lowest temperature? In fact, what happens at absolute 0? Our simple equation for entropy breaks down. We can't divide by 0. Neither the first nor the second laws give us a way to tell how entropy is going to behave at absolute 0 when temperature equals 0. For an ideal gas at absolute 0, temperature equals 0, so PV also has to equal 0. Remember that entropy depends on the range of speeds and the scale of the volume that are available to the molecules in the system. If the molecules have no temperature, that means they have no kinetic energy. They have no internal energy. They're not moving around. And they also have no volume in which to move. So we can reason that for an ideal gas, entropy equals 0. That's fine for an ideal gas, but is it the same for real atoms and molecules? Well, this is one case where our intuition from ideal gases fits a wide number of cases. Using statistical mechanics, Ludwig Boltzmann showed that entropy is equal to Boltzmann's constant times the ln of a value omega, where omega is the number of possible microstates that a system can take. A microstate is just another way of counting the different positions and velocities available to the molecules. At absolute 0, there's no thermal motion. And while the molecules do take up some volume, the volume will still be as small as possible. So if we can imagine a perfect crystal, one in which all the atoms are the same, and the crystal they form is perfectly repeating in all dimensions, then there's only one way to arrange such a perfect crystal, and S equals Boltzmann's constant ln omega, where omega equals 1, means that the entropy is equal to 0 joules per Kelvin. Or in other words, the entropy of any perfect crystalline substance is 0 when temperature equals 0, which is a statement of the third law of thermodynamics, a relationship between temperature and absolute entropy. This rule establishes a physically meaningful 0 point for entropy, which means that we have a common point for measuring a standard entropy for various substances. Just like the standard enthalpy of formation lets us apply Hess's law to determine the standard enthalpy of reactions, we can use the standard entropy of substances to determine the standard entropy of their reactions. For example, we can find the standard entropy of hydrogen combustion to create liquid water at 298 Kelvin by using the standard entropies. Hydrogen gas equals 130.7 joules per mole Kelvin. Oxygen gas equals 205.1 joules per mole Kelvin. And liquid water equals 69.9 joules per mole Kelvin. So the change in entropy for the reaction is the standard entropy for the water, the products, minus the standard entropy of the reactants multiplied by their stoichiometric values, which gives us a total change in entropy for the reaction of negative 163.4 joules per Kelvin. Now there are two things to notice in this answer. First is that the standard entropies of oxygen and hydrogen gas are not zero. Unlike enthalpy, where we had to pick a 0 point and measure all the relative enthalpies of formation from that point, entropy is absolute and applies to all substances, even elements in their standard form. So entropy is only zero at absolute zero, and even then only for perfect crystals. The second thing to notice is that the entropy of reaction is negative, meaning that the entropy goes down for this system during the reaction, which makes sense because the volume occupied by the liquid is so much smaller than the volume occupied by the mole and a half of gases. Less volume means lower entropy. But the negative entropy implies that it's non-spontaneous, that the reverse reaction, water splitting into hydrogen and oxygen, should be spontaneous, even though we know that's not the case. Water is not spontaneously splitting into hydrogen and oxygen all around us, but hydrogen combustion is definitely a spontaneous reaction. Here's where we need to remember that the second law of thermodynamics doesn't just talk about the entropy of the system, but insists that the entropy of the universe has to be greater than zero for a spontaneous reaction. We also need to consider the change in entropy of the surroundings produced by the release of heat during the combustion process. We'll look at an example problem in our next video. Come on, get out of here.